At 5:12 a.m. on April 18th, 1906, a magnitude 7.9 rupture split nearly 300 miles of California while San Francisco slept. The shaking lasted barely a minute. The fires that followed burned for 4 days, destroying up to 95% of the city. Officials suppressed the true death toll. The world saw nothing but ruin. But this disaster didn't just devastate a city. It overturned everything humanity believed about why earthquakes happen, and launched a scientific revolution whose unfinished warnings still hang over California today. The first sign was a sharp jolt, a foreshock felt at 5:11:40 a.m. that roused a handful of early risers across the Bay Area. 20 seconds later, at precisely 5:12 and 3 seconds Pacific Standard Time, the main event began. Seismographs at Lick Observatory in Berkeley captured the initial pulse, their ink traces spiking as the P wave swept through the ground. Telegraph operators logged the exact minute the shock hit, their dispatches matching the instrument records down to the second. The rupture tore through the San Andreas Fault with astonishing speed. In less than a minute, nearly 300 miles of the fault broke open, from just northwest of San Juan Bautista to the remote forests of Cape Mendocino. The strongest motion lasted about 42 seconds, measured by the interval between the first seismic surge and the fading S-waves on the Lick Observatory's horizontal pendulum. Eyewitnesses described over 40 seconds of violent tossing, a sensation confirmed by the relentless movement on the seismograms. Field surveys later measured the consequences. The Earth had shifted horizontally by an average of 10 feet, with the largest single jumps, up to 20 feet, recorded near San Juan Bautista. Fences, roads, and even streams were offset overnight. The rupture's total length, calculated by triangulation surveys and later confirmed by modern GPS, measured 296 miles. International stations in Tokyo and London picked up the P waves 8 minutes later, providing a global timestamp for the event. The intensity of shaking varied with the ground beneath. Downtown San Francisco and Santa Rosa, built atop soft, waterlogged soils, experienced the most violent motion. Outlying towns on firmer ground reported less severe effects. The first aftershock, a magnitude 5, struck at 5:14 a.m., just minutes after the main rupture, signaling that the sequence was far from over. These precise records, drawn from instruments, telegraph logs, and field measurements, offered the first detailed look at how a great earthquake unfolds, setting the stage for a new era in seismic science. Flames erupted from broken gas mains and toppled stoves within minutes of the shaking. Downtown San Francisco, already battered by the quake, became an open furnace as more than 30 separate fires ignited across the city. Firefighters raced from blaze to blaze, but the city's water system had failed catastrophically. Over 200 water mains lay ruptured beneath the streets. Hydrants sputtered dry, hoses dragged limply over cobblestones, and the few remaining reservoirs could not reach the burning districts. Desperation led city officials to dynamite entire blocks in hopes of creating fire breaks. The plan backfired. Some explosions set off new infernos, while others scattered flaming debris into nearby neighborhoods. The infamous ham and eggs fire began with a spilled vat of grease and a stray spark, then swept through municipal buildings, destroying City Hall's West Wing and gutting block after block. For 4 days, fire raged, unchecked. Wooden sidewalks, warehouses, and tightly packed homes fueled the advance. The flames leapt Market Street and raced up Telegraph Hill, leaving only blackened skeletons where entire neighborhoods had stood. By the time rain finally dampened the embers on April 22nd, the numbers were staggering. Between 80 and 95% of San Francisco's destruction came from fire, not the quake itself. Nearly 500 city blocks and 25,000 buildings were lost. The devastation overwhelmed not just San Francisco, but also Santa Rosa and San Jose, where collapsed water tanks and single-source reservoirs left firefighters helpless. Engineers later traced the scale of loss to a simple truth. The city's lifelines, water, fuel, and fire response, were never built to withstand such a disaster. The firestorm revealed the city's greatest vulnerability, turning a seismic event into an urban apocalypse. San Francisco's leaders faced a second crisis beyond the flames, the threat of panic and financial collapse. Within hours of the disaster, city officials began shaping the public narrative. The first official death toll, 375, was calculated not by counting bodies, but by weighing the risk to property values and investor confidence. Behind closed doors, the mayor's office issued instructions to the coroner to keep casualty numbers low, to avoid alarming headlines, and to suppress details that could undermine the city's future. Newspaper editors received quiet warnings from police and city hall. Early editions with higher death counts were pulled from circulation, and journalists who pressed for details found their access restricted. The human cost, meanwhile, became harder to hide. Entire families vanished in the inferno, their remains buried in mass graves at the city's edge or in hastily dug trenches in Golden Gate Park. Coroners' ledgers and burial registers, later reviewed by outside auditors, revealed hundreds of undocumented burials, especially among the poor, immigrants, and the city's Chinese community. In Chinatown, survivors reported that many victims were never officially recorded at all. Relief supplies flowed first to established neighborhoods, while immigrant districts waited days for food, water, and medical care. Red Cross and Army records show that white, middle-class areas received most of the available aid, while marginalized communities were left to fend for themselves. The gap between official reports and lived reality grew impossible to ignore. Citizens demanded an honest accounting, and outside observers, including physicians, clergy, and visiting journalists, began documenting the true scale of loss. The push for transparency and fair relief soon escalated into calls for a formal, independent investigation. The city's attempt to control the story only deepened suspicion, setting the stage for a state-commissioned inquiry that would transform not just the understanding of the disaster, but the science of earthquakes itself. At the turn of the 20th century, earthquake science was little more than a scattered collection of observations and educated guesses. Across California, only a handful of seismographs operated, most of them at universities or observatories, their delicate instruments recording faint squiggles on smoked glass or paper drums. There was no statewide network, no standardized method for measuring ground motion, and no clear way to compare data from one city to the next. Most earthquakes, even powerful ones, left behind only stories and cracked walls. The San Andreas Fault itself had only recently been recognized as a distinct feature, mapped in broad strokes by geologists like Andrew Lawson, but its true nature remained a mystery. Many scientists still believe that earthquakes were random, isolated events, or that the shaking itself created the faults. There was no consensus on what actually caused the ground to rupture, or why some areas suffered more than others. Theories drifted between vague notions of underground explosions, shifting magma, or the slow settling of the Earth's crust. Seismology, in 1906, lacked the tools to test these ideas. Instruments were sparse. San Francisco had no permanent seismograph of its own, and most towns relied on distant stations like Lick Observatory or Berkeley for any record at all. Even where instruments existed, they varied widely in sensitivity and calibration, making it nearly impossible to compare results. Field investigations were informal, with scientists relying on eyewitness accounts, damaged buildings, and the visible scars left in the landscape. There were no protocols for mapping fault traces, measuring displacement, or cataloging aftershocks in a systematic way. This absence of standardized methods left critical questions unanswered. Why did some neighborhoods collapse while others stood firm? What role did the type of soil or underlying rock play in amplifying the shaking? Without consistent data, even the most basic patterns remained hidden. The destruction of San Francisco, Santa Rosa, and San Jose offered a grim laboratory, but the scientific community lacked the means to extract reliable lessons from the chaos. The limitations extended beyond instruments. Communication between disciplines was minimal. Geologists, engineers, and physicists each worked in their own silos, rarely sharing findings or coordinating fieldwork. Published reports were often anecdotal, filled with sketches and personal impressions rather than quantitative measurements. The few existing maps of earthquake damage were hand-drawn and imprecise, offering little guidance for future construction or disaster planning. In the aftermath of the 1906 quake, it became clear that science was unprepared to answer the most urgent questions. The scale of destruction demanded a new approach, one that could move beyond scattered observations to a coordinated, data-driven investigation. With entire cities in ruins and the causes of devastation still uncertain, the need for rigorous, systematic study was no longer theoretical. It was a matter of survival for the growing cities of the West Coast. This moment of reckoning set the stage for an unprecedented scientific response. The gaps in knowledge laid bare by the disaster would soon drive the creation of the first integrated earthquake investigation in American history, a turning point that would transform the study of earthquakes from a collection of curiosities into a true science. Andrew C. Lawson, a geologist at the University of California, Berkeley, stepped into a landscape of rubble and uncertainty with a mandate unlike any before. On April 21st, 1906, just 3 days after the earthquake, Governor George Pardee signed a special appropriation authorizing the creation of the State Earthquake Investigation Commission. The legislature allocated $75,000, a significant sum for the time, and charged Lawson with a clear directive: assemble a multidisciplinary team, document every observable effect of the earthquake, and produce a comprehensive public record. Lawson wasted no time. He brought together geologists, engineers, physicists, and surveyors from across the country, including experts from Stanford, Johns Hopkins, the U.S. Geological Survey, and several observatories. Field parties set out in coordinated teams, each assigned to map fault ruptures, catalog ground displacement, and interview witnesses. Their protocols, developed on the fly, became the first standardized procedures for earthquake investigation in the United States. Teams carried base maps, measuring tapes, compasses, and notebooks, recording not just the dramatic surface breaks, but also subtle shifts, offset fences, twisted rails, and the pattern of collapsed buildings. The commission's approach was exhaustive. Surveyors retraced property lines and triangulation benchmarks, comparing cadastral maps from before the quake with the new fractured landscape. Engineers measured the tilt of toppled chimneys and the angle of sunken piers. Geologists dug boreholes to examine soil profiles beneath the worst-hit neighborhoods. Every observation was logged, photographed, and cross-checked. In the field notebooks, one finds sketches of offset roads, tables of displacement, and first-hand accounts from survivors. Lawson insisted on rigorous data collection, recognizing that only hard evidence could cut through rumor and speculation. The commission's work extended far beyond San Francisco. Teams surveyed the entire 296-mile rupture zone, from San Juan Bautista to Cape Mendocino, documenting variations in slip, ground deformation, and the distribution of aftershocks. In towns like Santa Rosa and San Jose, investigators correlated the severity of damage with the underlying geology, noting that structures on soft, waterlogged soils fared far worse than those anchored to bedrock. These systematic observations laid the groundwork for understanding why some neighborhoods were obliterated while others survived. By 1908, the Commission's findings filled 2 massive volumes, over 1,000 pages of maps, photographs, data tables, and analytical essays. The Lawson Report, as it became known, was published by the Carnegie Institution of Washington. It set a new standard for disaster science, providing the first integrated, government-sponsored earthquake investigation in American history. The report's detailed mapping of fault displacement, its correlation of soil type with destruction, and its catalog of aftershocks offered a template for every future seismic study. Lawson's leadership transformed chaos into knowledge. The Commission's methodical pursuit of evidence, its insistence on transparency, and its commitment to public dissemination institutionalized a scientific approach to catastrophe. The stage was now set for Harry Fielding Reid, whose analysis of the Commission's field data would soon upend the world's understanding of how earthquakes work. Harry Fielding, Reid stepped into the aftermath with the question that had stumped geologists for decades. What actually happens inside the Earth when a fault like the San Andreas ruptures? Drawing on the Commission's meticulous field data, Reid began comparing pre-earthquake property surveys with the landscape left behind. He found fences bent into gentle curves, then snapped and offset by as much as 8 or 10 feet. At Bolinas, a wooden fence once ran straight across a pasture. After the quake, it was shifted sideways by nearly 3 meters, a visible scar captured in one of the investigation's most famous photographs. Reid's approach was methodical. He measured these offsets against old cadastral maps, charted the precise displacement at dozens of points, and cross-checked with triangulation benchmarks. The pattern was unmistakable. For years, strain had built up silently on either side of the fault, deforming the ground like a stretched spring. When the rupture came, the land snapped back to its original shape, releasing all that stored energy in a single, violent instant. In 1910, Reid published his synthesis, the elastic rebound theory. For the first time, earthquake science had a quantitative law. Faults store elastic strain, then release it in sudden jumps, driving the earthquakes themselves. Reid's insight transformed chaos into clarity, turning field evidence into the foundation of modern seismology. Maps drawn after the 1906 earthquake revealed a striking pattern. Neighborhoods built on soft, water-saturated bay fill suffered far greater destruction than those anchored on bedrock. The Lawson report's detailed overlays showed that ground shaking intensified dramatically on reclaimed land, toppling buildings and rupturing gas lines in areas like the Marina and China Basin. This was not just a matter of poor construction, it was the soil itself amplifying the seismic waves. Engineers and geologists traced the worst collapses and fires to these zones, while structures on firmer ground often remained standing. Decades later, the 1989 Loma Prieta earthquake confirmed this early insight. Once again, the Marina District, built atop the same bay fill mapped in 1906, experienced the most severe shaking and catastrophic building failures, even though it was miles from the epicenter. USGS ground motion records from 1989 showed peak accelerations on bay fill up to 3 times higher than on neighboring bedrock. The predictive power of those first soil damage maps became undeniable. Today, seismic hazard zoning across California relies on these lessons, using soil type as a key factor in building codes and emergency planning. The ground rules for urban survival were written in the aftermath of 1906, and every new earthquake puts them to the test. The San Andreas Fault beneath California remains locked, storing strain measured today by dense GPS networks, roughly 20 to 30 millimeters per year along the central segment. This slow, relentless movement is invisible on the surface, but it marks the countdown to another rupture. The lessons of 1906 are embedded in every modern safeguard. Building codes across the Bay Area now require seismic retrofits for unreinforced masonry, strict drift limits for new construction on soft soils, and mandatory site class assessments. These rules stem directly from the soil damage maps and ground motion records first compiled after the quake. Early warning systems like Shake Alert, operational since 2021, use real-time seismic data to deliver precious seconds of advance notice, enough to halt trains, slow elevators, and trigger emergency protocols. Yet even with these advances, the region's vulnerability persists. Hazard maps show that millions live and work atop zones that shook hardest in both 1906 and 1989. The fault is quiet, but not at rest. Each year, new data confirm that strain continues to build, and the science born from catastrophe now serves as the first line of defense against the next inevitable earthquake. The legacy of 1906 endures each time California measures soil, redraws zoning maps, or braces for the next rupture. Scientific truth, once buried by politics, now guides cities confronting fault lines beneath their feet. Today, more than 25 million Californians live near active faults. The question is not if another disaster will come, but whether we have the will to learn before history repeats itself. Share your thoughts below.